Hi, welcome to the video lecture on confidence intervals, the main part of it. Last week we did a little bit with confidence intervals in SPSS, but now we're going to look at two other confidence intervals, as well as the same one we did previously, but this time in StatCrunch. So the first one we're going to look at is the Z confidence interval from mu. So this week we're going to look at two confidence intervals for mu, and then one for the proportion. So the first one is the Z confidence interval for the mean, and we use this one when we know the standard deviation for the population. Now this really doesn't happen very often in real life, but occasionally it does. And so we cover this also because it has some connections with the central limit theorem. But I'm not going to ask you to do these by hand, so that's kind of going on behind the scenes. So this is an example where we have starting salaries for a random sample of 50 entry-level social workers. We get the sample mean of 42,500. And we have to assume we know what the population standard deviation is. It's 3,100. So we're going to go to StatCrunch, and we're going to pull up under Stat, Z-Stats. This is one sample with summary. Okay, so Stat, Z-Stats, one sample with summary. We're going to type in the sample mean, which we said was 42,500. The standard deviation, we said, was 3,100. That's based on a sample size of 50. And we want a confidence interval, and I'm just going to double check what level we said. We said we wanted 95%. So 95% confidence interval, click compute, and that's our output. All right, so I'm going to ask you when you do your homework to copy this and paste it to show me your output. So this is our output, and that tells us that our confidence interval is 41,640.74, the lower limit, to the upper limit of 43,359.26, which means that we're 95% confident the mean starting salary for all social workers, so this is in the population, is between those two values. Previously we talked about how to find the margin of error, but just to refresh your memory, we take the upper limit, subtract the point estimate, which here is the sample mean. So if we do 43,359.26 minus 42,500, we get the margin of error. So it tells us that our estimate is 42,500 with a margin of error of 859.26. Okay? So again, for this problem, it's for the mean, and we know the standard deviation for the population because they say assume the population standard deviation. Okay? So that's going to be an important distinction for us. So like I said, we use the Z confidence interval if we know the population standard deviation. If we don't, we estimate it with the sample standard deviation, and there's a slightly different formula that's based on the t distribution. So the Z confidence interval is based on the Z distribution that we've been talking about, whereas this one is based on a slightly different distribution. So the story here is that if sigma is unknown, like I said, we're estimating sigma, the population standard deviation, with the sample standard deviation. Since this estimate is not perfect, especially with small samples, we have extra variability in our estimate. So we use a distribution that's a little bit more spread out than the z distribution. And that's why we use the t here. And we mentioned this last week, but in order to use the t interval, we need to know that we have a large sample size, and we usually use 30 as the cutoff, or we know that the data follows approximately a normal distribution. And you can tell that usually by looking at a histogram, or they might tell you at the beginning of the problem to assume it does. Okay, so here's an example of a t interval. We have a sociologist wanting to estimate the average number of weeks between a couple's engagement and their wedding. So we have a sample of 16 couples with an average length of engagement of 19.92 weeks with a sample standard deviation. And notice this is the sample, so that's S. That means sigma is unknown if we're using the standard deviation from the sample of 5.73. They tell us to assume normality, which we need because our sample size is small, and they're asking for a 95% confidence interval. All right, so back to StatCrunch, and this time we're going to t-stats, one sample with summary, and we said the sample mean was 19.92. Sample size was 16. We want a 95% confidence interval, and I'm going to have to look up what the standard deviation was. 5.73 weeks. So 5.73. We want a 95% confidence interval, so we compute, and that gives us our output. So we have our confidence interval here. We're 95% confident that the mean length of engagement for all couples is between these two values. And the same way we did before, we've got the sample mean, so 19.92, plus or minus our margin of error of 3.0533. And we did the same thing we did before. We got that by doing the upper limit minus the sample mean. All right? Okay, so let's do another example. I want to show you one where we've got data instead of summary statistics. So we've got a sample of 10 neighborhoods in this example. And in each neighborhood, we've got the total acreage of space that's allocated to parks. All right, so here we have a list of data, and I want to point out here that this is a t interval because we don't know the population standard deviation. The standard deviation here is going to have to be calculated based on this data, which is a sample. All right, so if we go to StatCrunch, I already typed this data in. So we just have to go to t-stats, one sample, this time with data. So we pick our data. We want a confidence interval, and we want a 90%. If you want to check normality, that's what some of these are. We could look at a histogram, but you're told in the problem to assume normality, so we can just go with that. So click compute, and that gives us our confidence interval. And from there, it's the same interpretation that we've seen before, and the same sample mean plus or minus the margin of error. All right, so that's the t interval. Now that we're finished with the two confidence intervals for the mean, and now we need to look at the one for the proportion. So this is a new statistic parameter pair for us. So the population proportion, which is a parameter, is denoted with a p, usually lowercase p, but it doesn't really matter. The sample proportion is a p with the little hat on it, and we literally pronounce that p hat. Okay, so p hat is our point estimate for p, the sample proportion being the best estimate for the population proportion. All right, so to calculate the sample proportion, we just take the total number in a sample with whatever characteristic we're interested in and divide it by the total number in the sample. So if we have a sample of 200 people and 48 of them are left-handed, that sample proportion is going to be 48 out of 200. It helps a lot if you see if you can rephrase your data as x out of n. Here we've got 48 out of 200. And that's going to be a clue for you that what we're looking for is the proportion and not the mean. So let's do an example here. So we've got a random sample of 200 young professionals, and we find that 24% take public transportation to work. We want to do a 99% confidence interval for the proportion. Now here we can't phrase this data as 24 out of 200 because this is a percentage. So we need to actually do the percent. So we need to do 0.24 times our out of 200. So that's 48 out of 200. Okay? So when we go over to StatCrunch, we're going to Stat, Proportion Stats, one sample with Summary. Number of successes, that's x. So that's x out of n. So number of successes, here we had 48 out of 200. And we said we wanted, I believe, a 99% confidence interval for the mean. So 99%. And this gives you a couple of options here, but just leave it at the default standard wall. Don't worry about what that means. All right, so x out of n and then 99% confidence interval. Hit compute. And that gives us our output, which we can just copy and paste. And we get a lower limit of this and upper limit of this. So we're 99% confident that the proportion of all young professionals who take public transportation to work is between those two values. If we wrote that as a margin of error, it's going to be 0.24. So we always want to write that as a proportion. So even if they just give it to you as x out of n, we want to write it as the sample proportion. So 0.24 plus or minus the margin of error, which we're getting the same way we did before by doing the upper limit minus the point estimate. All right, so we'll continue this on part 2.